So the lecture 2, I'm going to talk about, yesterday I mentioned that it's a strategic network formation, stability versus efficiency. And we are mainly going to talk about TU games. So before talked about stability versus efficiency, as I mentioned yesterday, we have to know about little bit about TU games, communication situation, network games, along with their allocations rule. Okay, so let's see. So today I'll try to cover what is a game theory, what is a cooperative game, and different kind of allocation rule. Okay. So let's see what is a game theory or decision science. So the first, here I have mentioned one definition, the standard definition. What is this definition? That it's game defined a situation where it involvement of different multiple agents, that they are abide by some rules, set of rules, they have to abide by this set of rules, and there are some possible movements are there for each agent, and in return there will be some outcomes for each possible movements. So this is a standard definition. So basically what is a game theory or decision theory? It's a modeling of human interaction in social and economic situation. Right? So game theory, what does it do? Actually, it mainly it's a study of human interaction in different situation. Okay. So earlier first he started human interaction, human behavior. Then now it is started to study about animals' behavior also. So as I mentioned about that the agent. So what could be an agent? So agent could be any country or individual, firm or companies like. And so mainly in game theory, what they're trying to do, we try to study their behavior in a different situations like conflict and cooperation situations. And it is assumed that these agents, they are always rational and intelligent. So what do you mean by rational and intelligent? So this means that they always try to, their objective is to, so they are intelligent enough to know the whole game, and their objective is always try to make their outcomes. So they try to optimize their outcomes. Okay. So first, as I said, there are some agents. So n numbers of agents are there, right? As I said, they are always rational and intelligent. So based on their situation, whether it is conflict or cooperative situation, they have to abide by some rules, and some actions are available to them. So there are some actions, or I can say some strategy are available to them. Say M strategies are there, and now based on the scenario, what is the scenario or situation, they have to take some decision, or there should be some movement. Okay, so there have some action, they have to take decision, or they have to take some movement. Say it is a P, some movement. Right. So now once they decided something, take the decision. So there should be some outcomes. Right? So corresponding each action, there is always a different outcomes. Okay? So now, as I said, the situations are like always conflict and cooperation, right? So what do you mean by conflict and cooperation? Say, here I have mentioned some example. So we can talk about, say, competition among different firms. So in a business or market, you have seen that always these companies are in a war. Like, so like this Apple versus, we can talk about that Apple versus Windows, right? iPhone versus Android. This is some good examples are complex situations, right? So that between conflict between management and labor. Okay, these are one conflict situations. These are some example of conflict situations. Now let's see what kind of cooperative situations are there. Okay, let me tell you one thing, that in this conflict situation, always player try to play individually. So they will have some strategy, right? Each company or firm, they have some strategy and they try to choose their best strategy so that they will get more outcomes. They can optimize their outcomes. Okay. So then what is a cooperative situation? The cooperative situation I can give you like the merging of two companies. So we have a different examples of merging two companies. So when two companies are facing crisis, financial crisis, and they decided to merge together and they start working together so that they invest more and then they can earn more. They can optimize their profit, right? So for example, this VI, probably you have know about this VI, Vodafone and Idea merging, they merged together. And then the Tata groups. So Air India was facing a lot of crisis and during COVID, it became worse. So after that, Tata group, Ratan Tata bought it. So probably you have know about it, right? So then Ratan Tata is trying his best to break the glory of Air India. Now later he announced that this Vistara and Air India, they both are going to merge. Okay. So this is the situation when the agents or any they try to cooperate others so that they can optimize their outcomes, right? So here we have two kind of scenario, conflict and cooperation. Based on this scenario, a player, this agent behave differently. So as I said, in a conflict situation, player always play individually. They have strategy, actions are there, they have some strategy and they try to choose their best strategies so that they will gain more. But in cooperative situation, their strategy is what? They make coalitions. They will try, they don't play alone, they try to play with another's agents. They will have some binding agreement that they are going to play with another player so that they will gain more. Okay. So now this kind of scenario, based on this scenario, we have a different type of games. As I say, for the conflict scenario, the behavior we study is we define the game, it's called non-cooperative game. So they play alone, they have strategy, right? So in a cooperative scenarios, if we define a game, it's called cooperative game. Okay. So today I will going to talk about only cooperative game, right? And so these are three representative form of games: strategic, extensive and characteristic. The first two are used for non-cooperative and we usually use characteristic function form to define a cooperative game. Sorry. Any question you have? Okay. So as I said, say a game is a simply, there should be some involvement of some agents and based on the scenario, what is the, there are some actions are there and they have to decide something and based on whatever they are going to decide, there should be some outcomes. And these agents are so intelligent and rational, their agenda is only that they will try to optimize their own profit. Okay. Okay. As I said, in a cooperative situation, so players' strategy is to make coalitions. So they have some binding agreement, they will work so that they will work together to gain more outcomes, right? So here what is the strategy? That they will form coalitions. So if I have this n number of agents, so they, as I said, they will form some coalitions, or coalitions means it's actually subset of n. So any subset of n, they are will trying to form and this subset are we call as a coalitions. Okay? That is important. That what do you mean by coalition? That is important to us. So after that, once they formed a coalitions, then let's see how we mathematically define a cooperative game. Okay. As I said, if we have n numbers of player set or agents, so we have a 2 to the power n we can define as a set of all coalitions. So how many coalitions do we have? Yeah, 2 to the power n. We consider 2 to the power n minus 1. So we remove the empty coalitions, the empty subset. We don't consider the empty subset. Okay. Okay. So we define how we mathematically define a non-cooperative game. So it has a pair n and v. So n is the player set. So what is v? So once the coalitions are formed, so there are some lot of article how these coalitions are formed. There are a lot of articles, so that I'm not going to discuss. But as I'm saying that once the coalitions are formed, so then we define a function v on what is the domain here? The set of all coalitions. So it's a real value function with the restriction that v of empty is 0. V of empty coalitions, that, yes?
So in the set of coalition, do we count the coalition of the player with itself?
Yes, yes, individual also, yes. Yeah, yeah. We consider everything. Yeah. Okay. Okay, so this pair n and v together, n is the player set, together any value function, this function v, that is the domain is all the set of all possible coalitions, together we call a cooperative game, right? Okay. Okay, next we say Zn. What is a Zn actually? So on Zn, so n is given the set of players. So now all possible cooperative games on n is denoted by Zn, right?
It consists of all the value functions.
Yeah, value functions, right? Value function on n is fixed here.
So it consists of all the space of n comma v.
Yes, different v on n.
N is fixed.
N is fixed, yeah. Yeah, n is fixed and all possibles, we are going to consider all possible v on n. It makes a linear space. This space, the set of all possible games on n, it is actually a linear space. So where the operators are it will be like under this operator. Okay, this is V1, this is V2. Simply addition and scalar multiplication. So where this alpha and beta are scalars and V1 and V2, the two different games. Okay? To the power n, yes, minus 1, yeah. Okay, this is actually the typo, it is actually 2 to the power n minus 1, that is the dimension, yes. This is not 2 to the power n minus 1, 2 to the power n, then minus 1. So we have to remove that empty, yeah. Okay, any question you have? Okay, now this is a linear space, let's talk about this basis. So we have a 3 different kind of bases here. So one game we call unanimity game. So let's see how it's defined. It's a one kind of basis for the linear space. So it's actually So for any S, it's a non-empty coalition, okay, 1 if S contained in T and 0 otherwise. Okay. And then we can represent V as a some coefficient alpha S and those unity games. Okay, sorry, here we have to set S. Okay. Where this alpha S coefficient can be defined as a should be non-empty and it will be minus 1 to the power the cardinality of S minus cardinality of, do you know what is the cardinality of a set, right? It's a numbers of element in that set. So that's how we define the coefficients. These alpha S coefficients are also called unanimity coefficients. Okay.
What is the domain of US?
Domain of US is actually a kind of, yeah, GN.
And so in both the cases, S is a subset of N.
In both the cases, S, yeah, S and both T and all are subset of N, all are coalitions. Okay. Any question you have? So there is a one interpretation regarding this unity game. So let me tell you what is the interpretation is that, suppose there is a one group. So there is a one, say, cake is here. And we have to distribute this cake. There are some different groups are there. Say we have probably some group. And somebody said that this, say, will get the cake only to one group of the people. Say we have a 4 groups are there. So let's T1, T2, T3 and T4. There are 4 groups are there. Now somebody in T1, he gets the chance to distribute the cake among these all groups. Okay. So what he is going to do? Yes. So then he definitely try to maximize it, right? So and there is a one restriction that these cake or whatever only one group will get. If somebody get the chance, someone here, say in T1, get the chance to distribute the cake or give the cake, to whom group he will choose? His own group, right? Yeah. So this is the story behind this that Ash, if that we assign 1, that means somebody is some amount is there, say 1, and we have to distribute the amount to the group. So we choose that group so that S belongs to that group, right? Okay, it's clear? Okay. Okay, so now once the game is formed, that the coalitions are formed, we define the game. Now the question is how we are going to distribute the outcomes, right? So there are main assumption we consider always that the word Vn, the grand coalition, that N is the player set, and Vn we call is a grand coalition that will always form. Okay. So now our question, how we can distribute this grand coalition among the all players in a fair and efficient way. Grand coalition, I said that V is a function on set of all possible coalitions, right? So N is the player set and Vn is the grand coalitions, means the whole player set N. The Vn is actually is what of that N. Once the whole N. Yeah, we assume that is always forms. As I said, the fair way, I will come to do what is a fair way, but what is the efficient way? So efficient way is that we try to distribute the worth of Vn among the whole players. So whatever they are going to get in that allocation rule, the sum should be V of n. So efficiency here, the efficient way I said that what is the efficiency here? That allocation for all player should be equal to worth of the grand coalition. This is the one efficient way we have to do the allocation. Okay. So there are a lot of allocation rule that was described, that was introduced in the cooperative game theory. So one is Shapley value. So it has a lot of huge application, then core solution, Banjab value and many more. So here I am going to discuss 4 types of solution. First, core solution, Shapley value, Banjab value and equal division or egalitarian. So this type of 4 allocation rule that I want to discuss. Okay. So here I have one simple example, very simple example of a cooperative game. Suppose there are 3 friends, 1, 2 and 3, right? And say they walk together or they went for a movie or somewhere. So now when they want to return, so they, so this is a starting point and they lived in the same different way, say walk together and then when they were returning to home, say they lived in these places, player 1 in here, player 2 here and players 3 here. Now what they did, they booked a cab, right? And so total fare from starting point to the player 3 destination is 200. From here to is 90, it is 150, right? So what is the best fair way we can distribute this amount of money how they are going to pay it? One fair way is what? From this point to this, they will divide it by 3, equally they will divide it, right? And this is the destination for player 1, right? So this is the destination for player 2. Some point this to this, player 2 and 3, they are traveling together. One is not traveling in that route. So the amount of money from this 150 minus 90, then that amount we are going to distribute among 2 and 3, right? So now here only player 3 is traveling alone. The rest of the money, that is 50 rupees, that the player 3 will pay alone. This is the one fair way to pay the money to the cab driver, right? Okay. So based on that, this is the scenario. So based on that, I define a game V is actually the total cost fare, total fare from 1 point to 3 point, another point. Say V1, actually what? It is 90 rupees. The watt for player 2 is actually 150. Watt for 3, it is 200. And 1 and 2, it is 150, 1, 3 is 1 and 3 is 200, P of 2, 3 is again 200 and P of 1, 3 is 200. Okay. So this is the example that I want to show. This is how we can construct a value function. We define a cooperative game. So this is a simple scenario. Okay. So next, so come to the safely value. So safely value, this is how we define the safely value. Okay. For each player, we assign a real value where it satisfies this efficiency condition first of all. Then the total total allocation for the safely value, total allocation should be equal to Vn. This is the first condition. Second, the linearity condition. Third, the null player, and fourth is anonymity and also monotonicity. Okay. So I'll come to this theorem later, but first of all, I want to explain that safely value. What does it mean? Okay. So safely value is actually what? So any player I, there should be this coefficient is there, is actually average of all its marginal contribution. So what is a marginal contribution? Suppose for the player I, any player in I, say he is in that coalition, right, and he is not in that coalition. Okay. Suppose a particular player I, he belongs to a coalition and he is not in the coalition. So what is the difference? The difference between the what when he was in that coalition and not in that coalition. That is called marginal distribution of particular player I. So it considers average of all its marginal distribution. Okay. These are cardinality of S. N is the cardinality of N. The simple cardinality. Okay. So this is a one expression, but earlier we have a different expression. So I am going to explain it. So what is the expression it has actually? So suppose this is the one room. We can talk about this classroom. Okay. Then so this is a player set N. So let's consider for the time being the people who are in this room. And if I ask them that to make a queue outside the room and to enter the whole classroom, right? So say that there is a one queue outside the room and our objective is to form the whole GAN coalition inside the room, right? So now, how many possible way we can and the queue can enter? N factorial way, right? You know N factorial? So N factorial way the queue can enter and form the GAN coalitions. Now, for any particular player in N, what actually safely value does? So each actually okay. So what is a safely value does is actually consider a particular player I in all possible N factorials. So it consider all possible N factorials and say for particular player I when the all player who are above him, I mean the line, he consider that marginal watt of that players minus when he entered the room, what would be the watt? So it consider all possible way and it will average it. So in case of say let's take one simple example, say 1, 2, 3, there are 3 players, right? So we have a 3 factorial way we can ask to form the coalitions, right? So let 1 is, for the Shapley value for 1 would be what? So for he can be in the first on the queue, then second in the queue, or in the third in the queue. So total we have a 6 possible, right? So then what are the marginal contribution for the player 1 here? So when he is the first in the queue, the whole room is empty. That means the empty coalitions, right? So then his marginal contribution with this. What is this individual vote? Minus 0, right? And when he was in the second position, what are the possibles? Either in the room, the player 2 will be there or 3 will be there. So we have 2 possibilities, right? Or right, these are 2 possibilities we have. Now, when he is the third number in the queue, what are the possibilities we have? So before that, either 1 can enter, then 3 or 2 or 2 or 3. These are the possibilities, right? So we have this. Right? So Shapley value is the average of all this marginal distribution. So this actually equivalent to this. Okay. So in case of simple this example, you can verify it. Okay. Okay. Now I have one quick question for you. So for this example, can you just try to find out, this is one simple example, can you just try to find out what would be the Shapley value? V is given to you. Now just try to find out. Okay, let me write you that expression for the Shapley value. Just try to, first just try this, write down in your copy, then I will just show you that expression for the Shapley value. Let me know when you are done. Okay. Okay, you can apply this expression here. I is the player. Yeah, so I could be anything, 1, 2, 3. So you have to, all of them, all of them. So when you are going to find out the Shapley value for the particular player 1, then it would be summation over just a minute, okay, it will be S E N, yeah, N could be everything, right? Right? Okay, okay. So I was thinking about another expression. Okay, in this expression it is fine. Yeah, you have to consider all subset of N. So it is actually like this. So it will be like the Shapley value for 1 by 6 V of 1, 2, 3 minus V of 2, 3 plus V of 1, right, plus, oh no, sorry, this is 1 by 3. This is 1 by 3 and this is 1 by 6. V of 1, 2 minus V of 2 plus V of one tray minus V of tray. Yeah, just you have to calculate all this. Similarly, you will have an expression, similar kind of expression for 2 and tray. So, what is V of 1, 2, 3 is 200, right? So, this is 200 is given, I think. 2, 3 is again 200. What is V of 1? This 90, yes. What is 1, 2? 150? It is 150. V of 2 is what? Again 150, right? 1, 3, 200 and this is 200. So, then it will be like 60 or 20. What's the final answer here?
How did we get 170? Yeah, that was it. Present 1/3, right?
Which one? Which one?
Equal to 1/3 into V of 1, 2, 3. Is that 1/3 actually?
Yes, 1/3.
This is equal to 3, right? This is 3. So 2 factorial by 3 factorial.
So, it is what? When n equal, s equal to say hold the gain coefficient n,
Small s is 3.
small s is 3, n equal to again 3. So, it will be what?
2 factorial.
Is it 2 factorial by 3 factorial?
Yeah.
This is 1 by 3,
Yeah.
right? 1 by 3.
0.
And when n equal s equal to only 1, then it is again 1 by 3. This coefficient will be 1 by 3 and yeah. Have you got any answer or anything for any particular player? So, here it will be like for the one player one will be all are cancel out. So, it is 90 by 3, right? This 3. So, similarly if you calculate for the player 2, for 2 you got something. So, for the player 1 we got is 30. If you are good at coding, then you can think about to, for a coding for safely value. Okay, so we got the player 1, the safely value for player 1 is 30, and let me tell you, because I have calculated for the player 2 it should be like 90 or, oh no, sorry, 60. Is 60 and the other player it will be 110. Right? This is the safely value, and we discussed one of the fair way we can distribute the whole fare among these 3 parents is what? 30, 60 and 110. And safely value gives us the same allocation. Okay. Okay. So you can do this verification in your home also after that. So now I want to say that there is this allocation rule, well, have to satisfy some axioms or some rules. So let's see what are the axioms it should satisfy. The first axiom should be, as we discussed, it is efficiency, that we allocate the worth of the gain collision among the players, right? Second, the linearity. So linearity actually scaling factor. So it sometimes we use in the exchange of money or something like that. So now second is actually important property, it's called null player property. So what is a null player property? Say suppose a player is contributing nothing in the game, right? His contribution is totally zero for all coalitions, then safely value gives him zero allocation. So some particular player is there in that game, he is participating, but his worth is almost zero. So whether he is in that coalition or not, it doesn't matter, the worth doesn't matter. So that means his contribution is totally zero, so then Shapley gives him zero payoff. The second is that anonymity property. What is the anonymity property? Is that suppose a particular player, say I and J, two player I and J, the distinct player I and J, their contribution is same in that game, right? Two different players, they are contributing say in in that game. So that Shapley gives him that equal allocation. So if you are playing or somebody very big person is playing, but if that your contribution with that person is same, Shapley treats him equal, right? Okay. So together with efficiency, linearity, null player, anonymity, we have a characterization with a Shapley. So if an allocation rule satisfies all these four properties, that we can say this is the unique allocation rule, right? So suppose there is a one allocation rule, any allocation rule phi we have, and this allocation rule satisfy these four properties, then we can say this is the unique allocation rule. This is the only allocation rule that satisfy these four properties together. Right? So this is a one axiomatization for Shapley value. So there are a lot of axiomatization for the Shapley value, but this is the original one. First it was introduced, and Shapley value has a lot of applications in airport game also, in queuing theorem also, and in biology also. Okay. Okay. Then let's move to another solution. It's called core solution. So this core solution a bit complex. Let me tell you why. Because most of the time we have a non-empty core. So I will see in which conditions we have a non-empty coreness. Okay. So how we define the core? So core we define that like this way. So it is as an allocation rule. We have some tuples such that is satisfied two conditions. First condition is we call efficiency. And second condition is that the whatever this core allocation for the any players which are in that allocation rule, they should be get more than worth of that coalitions. So here we have a one. So have you studied LPP? Linear programming, have you studied? So do you know about maximize function? Then you have some restriction function, and then you have to try to, find the allocation solution, right? Feasible solution. So here you can consider is a maximize objective function, and these are those constant. Yes, yes, exercise, yes. Yeah. Okay. Okay, this is the actually general definition. So I am just going to give you a, in case of three-player, what would be the core solution? Suppose we have this three-player 1, 2, 3, right? The core solution could be like this. So it will satisfy these conditions. So V of 1, that what of the coalition 1, then what would be the core allocation for the player 1 should be greater than what he is, generating alone. And similarly for the all individuals. For player 2 and 3, they will expect whatever they are generating alone. And when the summation of allocation for the player, core allocation together for the player 1 and 2, it should be greater than or greater than for when they are generating together 1 and 2. So similarly we have for 2 and 3, right, and should be the maximum of all xi, right. So together all these conditions we have a, we can define core solution. Okay. Okay. So that can, if we go back to this example, can we have a core solution here? Do you think this is a core solution, 30, 60 and 110? Is it satisfying all those constant and objective function? Right? I do agree or not? Right. Right. Why? Because according to the core solution, that this is 30, x1 is actually 30, it should greater than 90, V of 1, right. So it's not satisfying the core, all conditions, right. So can you have a core solution here? Like, so here we have the x1, if we think about it, say x1 is 90, x2 will be 150, right, it should be greater than 150, and x3 what will be? It is 200. But another condition was what? The maximizing condition, objective function is that it should be, sum of should be less than equal to 200. So here we don't have core, right? For this game we don't have core. So sometimes what happen, we don't have core. As I said that if we have a game, so we always have a Shapley value, but sometimes we don't have core. So core may be empty sometimes. So let's see for what kind of game we have a non-empty core. So here is a one type of game I have to mention here, that is convex game. So if game is convex, the core is always non-empty. So what is the game? we call a game is convex when if I have a two different coalition S1 and another coalition S2, and together what they are generating, that should be greater than equal to their individual payoff, individual watt minus the watt of those players who are common in these two groups. Okay, as I said, this is the intersection, right? So one way we can say, two different groups, whatever they are generating value, if they merge together, their value should be more, right? And minus whatever the common as players are generating. So this is actually expression is similar to the numbers of elements in a set, right? Do you know what is n, A union B is similar to this, right? Is equal to n of A, numbers of element in A plus numbers of element in B, A intersection B. This is almost similar, but this is strictly greater than equal. Right? So there is one theorem that if we have this kind of game, then that core is always non-empty. So here, can you construct a convex game? Just try to construct a convex game. So for T player also you can consider, because T player will take less time. Just try to assign some random number and so check whether this game is convex or not. So right now you don't need to think about that game, the interpretation of the game. Just find values of V so that it's satisfied for all S and S1, it satisfies this condition. Yeah, like that only, yeah. Like that only, yeah. Yeah, so it's a kind of additive game. Yeah, you are simply editing. Okay. Can you try to find a more complex one? Because it would be very easy to find a Shapley value and core solution. It would be 1, 1, 1 like that, right? Just try to find a more complex one. And on the, a little bit difficult, so that it's not an additive one. Last one 7. Okay. As you said, it's 7. Then what you said? 1, 2. Okay. So you said this is 1. Pairs are 3. Then it will be okay. Four. Right? So is it a convex game? See, it is like a 1, 2. If I say it is 4. Is it convex or not? So now then, can you try to find out the Shapley value for this game and the core solution, one core solution? So we can have, the Shapley is always unique. We always have a one core Shapley value, but in case of core, it is a set value. So we'll have a set of values, right? So we will have a more than one core solution. So can you just try to find out the Shapley value and the core solution here? So core would be 1. So you can think it is as a 3. So 2.5, 2.5 and 2. It's a 1 core solution here, right? So whatever the Shapley will probably like in between 2.25, no. No, it will be like 2.3, 2.33 and 2.33. It will be like this. Probably, I'm not sure, right? 2.3, 2.33, right? So now, as I said, for a convex game, the core is non-empty. And what do you think that Shapley value, this is also a core solution? Is it satisfying all the conditions of core? Are you agree or not? Is it violating any rules, any constraint or anything? No, right? No. Because there is a one theorem, when the game is convex, we have a non-empty core and this Shapley value belongs to core solution. Okay? Okay. So it's clear? Any question you have? No. So we have another characterization for this non-empty core, but that I don't want to discuss. So here this is a simple one, but this is actually not if and sufficient and necessary condition. So if the game is convex, then we can say the core will be non-empty. But if the core will be non-empty, we can't say that whether game is convex or not. Okay. Okay. So let's talk about, there is a one special kind of situation. It's called voting game, or there is weighted majority game. So what is actually voting game? A simple game. So suppose one bill has to pass in the parliament and each member has a some vote. I mean they have some or either we can say if they say yes, it will count as a 1, or they have we have some weightage for each member like that. W. Right? So a bill is going to pass in the parliament when then 2/3 of majority will say yes. Right? So here this we can say as a Q. Q votes. That Q votes we need to pass the bill. Right? Now, the game we can define as the bill will pass, that means 1, or bill will not pass, that means 0, either yes or no. So when the bill will pass, that the 2/3 of majority will say yes. That means the total weights of each player who are in S should be greater than equal to Q. As I said, the 2/3 majority, when the 2/3 majority will say yes, the bill will pass. Otherwise, it is what? 0. Right? And if the all weights of the player who are in I is greater than equal to Q, then we say that S is the winning coalition. And yes, for the winning coalition is 1. For the losing coalition means it is lose. It is 0. Okay. The scenario is simple. That bill is going to pass when the majority will say yes, right? So what is the two-third majority will have to say yes, and otherwise it will not pass. So this kind of scenario you can see the recent war and peace negotiations is that, like, we can talk about this Israel, the Hamas invasion in Israel, right? So, and then Ukraine. So UN was consistently trying to maintain the peace, right? So when the war is going to happen, so what UN do? What he does? So most of the country go against, or they try to oppose one country, and they try to support another country, like that. So if they support one country, so do you know about that recent Israel war situation? So India was indifferent, but they go against Israel. So that means, so when we have some courts queue to pass the bill, to implement the bill, there should be some courts. If the courts fulfilled, then the bill will pass. If it not, then it is no. So this kind of majority voting game we can see in the mostly war and negotiation phase, or in parliament also. So there are lots of articles also. Mostly they work on UN, European Union, and also I have seen there are some application of this kind of game in Indian Parliament also. Okay. So then the safety value we can define for this kind of scenario, and also there is another game value, it's called Banjab value, that is introduced for particular this kind of scenario. Okay. So let me express the Banjab value is actually divided by 1 by 2 to the power n minus 1, and so what is a Banjab value for simple game? It is called power index. We call it as sometimes Banjab power index also. Is actually the marginal contribution for the particular player I, and it is divided by 2 to the power n minus 1, simply. Okay. So it's a total number of, yeah, total subset of n minus is this average value. Yeah. So what is 2 divided by n minus 1 actually? No, it is not exactly that actually. It's just defined like that way. We don't consider I, or yeah, we can say like that way, that we are not considering that particular player I, that we are going to consider that there will be n minus 1 player, and it will be total number of coalitions in that set. It is 2 divided by n minus 1, including we are considering the empty, right? Okay. Okay, let me give you that characterization for this Banjab value. So as I said, this Banjab value will not satisfy this efficiency property. It does not satisfy the efficiency property. What is the efficiency property? As I mentioned, it should be the sum of the all allocation should be equal to Vn, what of the GAN coalition. So, but this particular allocation does not satisfy it. So that's why it is called a index, power index. Okay. So what are the other allocation it satisfy? Linearity, anonymity, as we mentioned, we discussed for the safely value, and then symmetry, linearity, and the third one again null player. So it satisfies these three axioms along with a one axioms that replace efficiency is actually called total power index. So what is this total power index? The sum of the all bunch of index for all players is actually what? 1 to the power n minus 1 summation, all S is a subset of n, non-empty subset we have to consider, and it will be B of S into numbers of players in S minus numbers of players in n minus S. It's just a technical, axioms. So it's not like the efficiency that we have some interpretation. It's just a technical axioms. When we sum of all the bunch of value, then it will get automatically this expression. Okay. Okay. Do you have any question till now? Okay, last allocation that I want to discuss is called egalitarian or equal division. So I discussed 4 type of allocation rule for cooperative game, right? So as I said, we are going to discuss about the strategic network formation, right, in networks. So that in the cooperative approach in the network games, so we'll see which kind of allocation rule is efficient, also pairwise stable. So for this 4 kind of allocation, it is introduced in network setup also. Then we'll try to find out, so among this allocation rule, which is both efficient and pairwise stable. Okay. So for egalitarian or equal division, it is very simple. Then what is a equal division? For any particular player, we simply distribute the worth of the gain coefficient among the player equally. So one example I can give you. So when the property is distributed from parents to among children, so in India what actually we do? So we equally distribute it among the children, right? This is what we do. Can you think about any other example?
In the taxi example, if everybody gives like
Yeah, equally, yeah, right. The 200 rupees, yeah, that's a equal distribution. Okay. So in that example, it will be like 200 by the taxi example, it will be like equal division will be 200 by 3 for each player. Okay. So now let's talk about this characterization. So first, it is efficient. Second, it is symmetry. Third, linearity. But fourth condition we can say is a nullifying player. It satisfies nullifying player. So what is a nullifying player? Say for any particular player, and so in the null player what happened? So whether that player in that coalition or not, it doesn't matter the what, right? Yeah, no. It will not satisfy this. But instead of that, it will satisfy something else that is called nullifying player. So what is a nullifying player? For any particular player I say, whenever he is in that coalition, the worth is always 0. In reality, it's very difficult to find this kind of example, right? So some particular player is like that. So whenever he is in that coalition, the worth is always 0. So for example, he is in the GAN coalition also, the worth is 0, right? So egalitarian value satisfy these conditions. Together, these axioms, efficiency, symmetry, linearity, and nullifying player, we can axiomatize the equal division. Okay. So this is about the cooperative game and allocation rule that I want to discuss. Do you have any question till now? Do you have any question? Okay, then I want to give you one homework. Okay, can you just try to construct some real life example of cooperative games? This is a homework for you. Say N and V, some real life example. So like that taxi example. Business dilemma is actually a non-cooperative. I am saying that cooperative because we are. That's a non-cooperative. That's a non-cooperative. They will play. Not right now. You can just try, think about it. Also tomorrow we can discuss if we have some good example. So for network game also we can extend it and then we can think about the pairwise and stability in that kind of example. So another example of cooperative game I can think, have you, most probably you have seen about it, buy 3, say get 1 free, this kind of scenario, right? So if there are 4 friends, they buy 3, they will get more, then what? They will have to pay less. So this kind of scenario, this is a simple example of cooperative scenario. So similarly, just can you think about a different scenario, cooperative scenario? At least we will have a say 4 or 5 example, then we can think about the stability and efficiency property somewhere.
Like referrals in a,
Hmm?
like if you refer someone in an app, you get a discount, and they also get a discount.
Right. So can you construct the V there? Just think about it, how you are going to construct the V. You,
V would be the total discount that both of them get, like V of the whole set.
hmm?
Yeah, and V1 would be the discount I get if I'm the person referring to the other person, and V2 would be the discount the other person gets.
So you mean that V of S is the what? Total discount of? Or it will be like, what is the discount?
Discount that the referrer gets is
Hmm?
equal to say the discount the referee also gets.
So this is referrer.
Referrer and referee.
Okay.
Yeah, suppose both of them get the same discount.
And you are going to equally distribute that among them? Or? Okay, if we have an odd number, then it will be okay. I mean, suppose because there is another player, so if I refers J refers K, then whatever the discount they got together, that you are going to distribute among equally. So like this is how you are saying, this is how we can construct the game. Just think about it, you can, I mean, if you have a good example, then we can discuss tomorrow. Okay. any more example, you can think about it. Yeah, definitely we have a network structure here, so we can think about a network game. Okay. But anyways, any cooperative game, we can construct a network games. Yeah, we can extend a cooperative game from a network game to a cooperative game to a network game. Okay, once you define the game, right? So just do one thing, try to find out the safely value, all allocation that we discussed. Not a bunch of value, you can skip, equal division, and trying to find out the core. Core might be non-empty or empty, it depends on the game, right? So just try to find out if we have a good kind of example. So. Okay, I just wanted to show you this, that there are a lot of work. These are the game theorists who got Nobel Prize. So in 1972 in Ken Arrow, then John Nash, as we have a Nash equilibrium that is quite famous. John Harsanyi, I saw that in the basis, so that's also called Harsanyi dividend. So this person, Harsanyi, he introduced that concept of Robert Oman, Roger Myerson. So tomorrow we are going to talk about his work on communication situation. That's an extension of cooperative game. Shapley value. So we talked about Shapley value. So he introduced this Shapley value. She got Nobel Prize in 2012. I think in 2016 he died in a car accident. These are the other person. Yeah. So a lot of people who got Nobel Prize in game, a lot of game theories got Nobel Prize.